Earthquakes are now reported as moment magnitude. So what happened to the Richter scale? Charles Richter and Benno Gutenberg developed the first magnitude scale in the 1930s to quantify earthquakes by relating the size or amplitude of seismic waves, shown on the right, plotted against distance as calculated from S minus P arrival times, shown on the left. Connecting the two gives you the Richter magnitude. The scale is logarithmic, so a 1 unit increase in magnitude corresponds to 10 times larger amplitude. The limitation was that seismologists measured certain frequencies, which meant that the signals from large earthquakes weren't adequately represented, like not being able to hear the bass notes on your laptop speaker. That meant that the Richter scale underestimated the size of large earthquakes. Seismologists have since developed far more sensitive seismometers that, with faster computers, have enabled them to record and interpret a broader spectrum of seismic signals. These improvements allowed them to better determine the energy released by large earthquakes. In 1979, they connected the seismograph recordings with the actual physical displacements that occurred during an earthquake. The result was the moment magnitude scale. Seismologists no longer look at only the amplitude of seismic waves, but instead use much more information contained in the seismogram to calculate what is called the seismic moment. The seismic moment, which defines how much force is needed to generate the recorded waves, is defined by this equation: mu times distance times area. Mu is rock rigidity. It describes the resistance of the rock to bending when force is applied and is a constant for a given rock material. More elastic energy is stored bending rocks of high rigidity than is stored bending rocks of low rigidity. For example, this brick has high rigidity and when bent or sheared would yield a strong earthquake. The cake has lower mu and shears easily. Rock rigidity is lower in the crust than it is in the mantle. As mentioned earlier, in most cases, distance and area can be determined by mathematical modeling of seismograms. D is the distance that the rock slipped along one side of the fault zone relative to the other side. In the 1906 San Francisco earthquake, this fence line was offset over 3 meters. A is the estimated area of the fault zone along which the rock slipped, the distance d. It defines the area that actually ruptured during the earthquake. Let's watch an earthquake happen. The arrows show forces building on opposing sides of a fault. Growing stress that will be relieved in the earthquake will be shown in red. Here we see blocks of rock move in opposite directions along a strike-slip fault zone, such as the San Andreas Fault in California. Potential energy, in the form of elastic energy, is stored in Earth's crust or mantle, building stress as the ground slowly deforms between large earthquakes. Take a look below the ground at the earthquake rupture that defines the seismic moment. That equation is then plugged into the moment magnitude equation, which is used by seismologists to measure the size of earthquakes in terms of the energy released, not just the amplitude of the recorded waves. The constants in the moment magnitude scale are chosen such that at smaller magnitudes, the moment magnitude matches the Richter scale. To truly appreciate this, consider the changes in the earthquake rupture required to increase the moment magnitude by 1 unit. Either the area of rupture or the slip distance, or both, must increase so that the product of slip distance times area increases by a factor of 32. While the amplitude of shaking caused by a magnitude 5 earthquake is 10 times larger than for a magnitude 4 earthquake, the energy released increases by about 32 times for each unit increase in magnitude. To understand the scaling, we'll look at the effects of the rupture area by using pasta as a model for magnitude. The cross-sectional area of a strand of spaghetti is about 1 square millimeter. When you break the noodle, it makes an earthquake of, let's just say, magnitude 5 for our model. Mu is constant for all strands of pasta, and for d, we'll use 1 millimeter of displacement across the fault. So here we see the pasta break and move laterally 1 millimeter. To increase it to a moment magnitude of 6, we multiply it times 32. The surface area is 32 times higher, yet the amplitude is just 10 times higher. To reach a magnitude 7, you have to multiply 32 times 32, and you get roughly 1,000 strands, or about a pound of spaghetti noodles. To get a magnitude 8, you need 32,000 pieces of spaghetti. A magnitude 9, on the other hand, would require 1,000,000 pieces of spaghetti. A magnitude 9 releases 1,000 times more energy than a magnitude 7 earthquake.